Today we consider the second order differential equations. Specifically, we consider only linear equations. You may know that first order differential equations are already difficult, and we don't know how to solve all first order differential equations. Same here. Second order differential equations are more difficult than first order differential equations, but we focus only on a very specific type of second order differential equations, what we call linear equations. And the type of equation we have is the following one. Here, A and B, they are just constants. So they are not functions. And the function f of s on the right-hand side is a given. We call those linear equations. So let me give you some examples. Look at those differential equation. You can see that this is a linear equation. A is -5 and B is just the function, f is s squared. After this class, you might know how to find all solutions of this equation. But let you know that this equation has not only one, but infinitely many solutions. When you say you solve this equation, you want to find all solutions, not just a particular solution, a special solution. You want to find all solutions. And after this class, you may know how to find all solutions of this linear equation. Of course, outside linear equations, we have many second order differential equations. And they may be difficult. For example, if you look at this one, you can see that the one right here is more difficult than the one we aim to consider, because right here you don't have constants. In here, A and B are constants. Right here you have s squared and s cubed, they are not constants. And it's more difficult. And we don't consider this one in here. Even though it's a second order differential equation, right? Or you may look at this one, but the right-hand side, you have something like this, you know. This is not a linear equation. This is not a linear equation. In linear equations, we are considering right here, the right-hand side is a given function, f of s. You should not see any y on the right-hand side. The unknown is only here on the left-hand side. And this is very difficult to solve. The one right here is difficult, and we don't consider it right here. So You may say that, all right, why do we consider linear equations only? In many applications, you see linear equations. A very simple example is when you look at a RLC circuit, and you find the current I in that circuit, RLC circuit. You may know that you get a linear second order differential equation in those some voltage right here. Let's say cosine of, let's say something, yeah. You know, this is a linear equation that we consider right here because RLC, they are just constants. So the right-hand side is the function. This is a function of t, but it doesn't matter, right? Now you may have s as the variable, you may have t as the variable. Yeah. So that's one more example. You see, in practice, we have linear equations. Let's go to the main question, how to solve linear second order differential equation. This is the main question we want to handle. When you look at linear equations, you may know that the right-hand side, f, of course, in zero, it can be any function. But let's say you consider the simple situation when f is always zero. Then it would be similar than the zero situation, right? Because of that, let's divide this into two situations. The first situation is when f is always zero. The second one is when f can be any function. We call the first situation right here, if you have an equation when the right-hand side is zero, in linear algebra, how do you call that equation? Yeah, so we call this one homogeneous equation. So if f is zero on the right-hand side right here, you call this equation a homogeneous equation, similar to system of linear equations in linear algebra. And the one right here is, of course, non-homogeneous equation. Of course, non-homogeneous equations are more difficult than homogeneous equations, since you handle any function f. So let's look at homogeneous equations first and see how to solve. And the good news right here is, in the end, you have a formula. It's like linear first order equations we already considered. In the end, you have a formula, or it's similar to quadratic equations you consider in high school. The formula you can find is the one you can open the note along with the assignment right here. So this is the note we have. And in the note, you may find this one. So this is the formula that we use in practice. But first, let me show you the idea behind this formula. For that, look at these examples as the motivation. Now you look at example 1 and example 2 because they are homogeneous equations. When you look at example 1, you will see that it's similar than example 2, right? What's special in example 1? In example 1, you see only the second order, the first order, but you don't see y, the zero order. In example 2, you see the second, the first, and the zero order. So they say the zero homogeneous equation. And this is special. This is a special homogeneous equation. Example 1 is extremely simple to solve. You can see how to solve example 1. You only need to set a new function u y prime. When u is y prime, then u prime is y double prime. And then this equation now is only a first order linear equation in u, right? In the new variable u, in the new function u, you have a linear equation, first order, and just apply the old formula. Right way you get u, so this from here to here is just about the formula we already knew. After you get u, how to get y? You just integrate u and you get y, right? So that's the end of example 1, right? So the idea is very simple. You just set a new function u for y prime, the first derivative, and then you get a first order linear equation. You easily get u, and after you get u, you get y. Just integrate u. Done. Now look at the second example. Of course, after you go through the second example, then you know how to solve any homogeneous equations. Because the second example is just an arbitrary homogeneous equation. Of course, now you cannot do the trick in example 1, right? If you set u y prime, then because of y right here, you cannot have the same thing. So how to handle the second example? The idea is that you can find a way, a different way, so that you can turn example 2 back to example 1. So what you try to do is you set a new function, let's say v or u or something, and in the new equation with that new function, somehow you can remove the zero order. You have only the second and the first order, similar to example 1, and then you know how to continue, right? For that, this is what I do. I set v equal e to the power negative 2sy. Now, the number 2 right here is not a random number. Where does the number 2 right here come from? Look at our equation. Let me copy the equation we have and show you. The number 2 right here is not random. When you look at this equation and then you associate this with the following quadratic equation, t squared minus 5t plus 6 equals 0. And you solve this one, you see the number 2. In fact, you have 2 roots, 2 and 3. Let me say again, when you have a second order linear differential equation, you just put the coefficients you have together, and then you get this equation, this quadratic equation. In fact, we have a name for this one. We call this equation the characteristic equation. The characteristic equation of this differential equation. You saw this characteristic equation. You see we have 2 roots, 2 and 3, and the number 2 in this set is that number 2. So let's see what happens after you set v equal e to the power minus 2sy. If you, of course, now you can have y just one, and now you know the next thing you do is you want to write the old equation we have now in the new function v. You can easily do that, and then in the end you see that in the new equation you see only the second order, the first order, and no v, no zero order. And this is exactly example 1, right? So you go back to example 1. In V, right? In Y, you don't have example 1, but in V, you have an equation similar to the one in example 1, and you know how to find V. And after you get V, of course, you get Y. And that's the end of the second example. And then you ask how to know the setting right here. How do we find this, the setting right here? How can we know that V equal just 1, and then it's simple also because you already got the motivation. The motivation is find a setting so that we can remove the zero order. Once you set that objective, it's not difficult to find a setting so that you can remove the zero order and get back to example 1. Yeah, so you may try with different setting, and then eventually you find one. So in 0, this is what you do. Let me write what happens when you have just 1. You had just 0 homogeneous equation. This is what you do in 0. You look at the characteristic equation. So t squared plus 8t plus b equals 0. And then you solve this equation. You may get t1 and t2. Of course, you may ask, how about when you solve this and you get no solutions? You always get at least one solution if you accept complex roots. So right here, if you say, all right, let's assume that we accept complex roots for this equation, then always you get at least one solution. Yeah, so therefore you don't need to worry about that. And then after this, you set, similar to the example right here, you set v e to the power minus t1 as y. If you do this one, now right here you have t1 and t2. If you want, you can write t2 right here, no problem, because you know it should be that. So in v, we get something like the one you see in example 1. We get something like v double prime plus some c v prime equals 0. C is a constant. And then, you can easily get v from here, right? Get v. This is just example 1. You just set u v prime, and then you get v. And then you get, of course, y. So this is the outline we have. If you know no formulas, if you know nothing, of course, if you apply this, in the end, you get the formula we see in the note. So this is the outline for solving the equation right here. Now let's practice this idea before we arrive at the formula. As always, in the end, we just apply formulas like quadratic equations in high school. it goes to understand the idea or the method. So let's look at one example in which we just apply this idea and solve the whole equation. Do you have any questions in here? Yeah. T1 and T2, they are equivalent. You can set T2 right here if you want. You can set T1 right here if you want. They both work. Because, you know, so the idea is we just pick up one solution. It doesn't matter whether you consider T1 or T2, they are equivalent. Yeah, so you can set T1 or T2, whatever you want. All right, so let's consider one example and see whether we can solve using the idea we have right here. So example, solve the equation. Just give you a very simple equation. So this one. First, this is a homogeneous equation because the right hand side is 0. Is it in example number 1? No, because in example 1, you had the second and the first order. Right here, you had the second and the 0 order. So this is something like in example number 2. And in order to solve this, we may go through this one and see whether it gives you own solutions. So let me put an answer to the question. So answer. First, I look at the characteristic equation. So I see we have t squared plus 4t equals 0. Sorry, 4, not 4t, 4 equals 0. This is the order 0, not the order 1. So this is the number 4, right? And then we solve this one. Do you see that you get 2? This time you don't get any real roots. You get 2 complex roots. They are what? 2i negative 2i. Do you know that? I already mentioned this. If you accept complex roots, you always get at least one root. And you don't need to worry about complex numbers. I right here is like any constant. I right here is what we call the imaginary number. It's like any constant. You have like 7 or negative 2 or anything. You just treat this one as a constant. It's not something special. It's like you look at real numbers, like 2.5, 6.7. If you imagine 2,000 years ago, you know, we would never consider real numbers like that. We just consider integer numbers. But then we see that real numbers are necessary, and we invented real numbers, and since then we just use it. All right, so let's continue. So if we follow this one, we set V. Now, right here, you had 2 rows. You may consider anything in here as T1. It doesn't matter. If you want, you can set this one as T1, this is as T2. Or if you want, you can set this one as T2 and this is as T1. So let me consider this one as T1. Then I have E minus 2isy. So I said v, the new function, this one. And now I want to see in the new function v, whether we can remove the zero order. In y, we had the zero order. But whether in v, you see only the second and the first order, no zero order. So let's check whether we have that. So then you want to write y as e to I as v, and then you differentiate. Why do we do this? We do this one because then we put this one back to the equation and see what we have in v, right? So differentiate y. Now, when you see I, just imagine that as a constant. Yeah, it's a constant, nothing special. So what you get right here is e to I as v prime plus 2iv. Now let's say you differentiate this one, you had this product. So first you differentiate v and you keep this one. And then you keep this guy v, but you differentiate this. When you differentiate e to the power 2is, you get e to the power 2is times the derivative of 2is. 2I is just a constant. So you get 2I. So this is the first derivative. Let's see what we have for the second derivative. So for the second one, you get e to I as v plus 2I Is that right? And then you get 2I as now 2I plus 2I is 4I, and 2I times 2I is minus 4. So we get the second derivative. You see the second derivative. And it's time to put it into this equation and see what we get in V, right? You want to see an equation in V. So now you get e to I as v double prime plus 4i v prime minus 4v. So this is y double prime plus 4y. This is y. 4y is 4v. And this is 0. 4v right here comes from 4y. So you can see now you have minus 4v plus 4v, you get 0. Keep in mind that e to the power 2is, this guy is always non-zero. How do we know that e to the power something is always non-zero? One way is that if you remember things about complex numbers, e to the power 2is is cosine of 2s plus sine of 2s times I. Do you remember that? And cosine 2s, sine 2s cannot be both 0, right? Therefore, this complex number is non-zero. Because of that, this guy must be 0 when you have a product. And it's equal to 0, and one of the terms, the factor is non-zero, then the order should be 0. From here, you get this one. And now this is exactly what we expected. We expect that after we set the new function v in the new form, we should have only the second and the first order, no zero order. And from here, you know how to find v, right? This is what we this is the objective, right? So now you just set. This is example 1, right? So you set u v prime, then this is u prime plus 4i u equals 0. And now this is just a linear first order equation. Right? Just apply formula. Apply the formula, we have, you get u right away. Do you remember the formula we have right here for u? Right, so in the end you get e minus 4is times c1. This is 0, so you have 0 ds, this is c1, right? After we get u, of course, we get v, right? V is just an antiderivative of u. So from here we get v. So v is just c1, and you get, you know, c1 plus some c2 is that right? I think now we get y. Y is just e to the power 2isv. So it's time to get y. Y is just e 2isv, and you get c1 minus 4i plus c2. Yeah. Is that right with y? So now you get the answer, right? C1 and C2 can be any constants. But when you have C1 an arbitrary constant, then C1 over minus 4i is also an arbitrary constant. Because of that, I think it's better to write C1 over minus 4i as only C1, right? Because this is just any C1. So from here you can write y as C1 from here to here, because I say that's because right here C1 can be any constant. Therefore, C1 over some constant is still any constant. So why don't we just have C1 right here instead of C1 over 4i, since C1 can be any constant. So this is the final answer we have. This is the final answer we have for y. And C1, C2 can be any constant. C1, C2 can be any constant. It means that when you solve this equation, you have how many solutions? When you solve this equation, you have infinitely many solutions. Because C1 and C2 can be any number. But all solutions you have should be given in this form. Now you may, this is the final answer, but you may want to write this in the standard form. You know, when you have e to the power is, you can turn it into cosine s plus I sine s. If you want to do that, then from here you can continue and write this one as C1 cosine of 2 s plus I sine of minus I sine of 2s plus C2 cosine of 2s plus I sine of 2s. You know that, right? In linear algebra, you may know that e to the power is is cosine s plus I sine s. And then this is just C1 plus C2 cosine of 2s plus minus C1i plus C2i sine of 2s. But when you look at this one, you see C1 plus C2 can be any number. And this guy can be any number also. Therefore, if you want, you can set this one as A, maybe N. This one maybe N. And then the final answer, if you want, you can write y in the form m cosine of 2s plus n sine of 2s, where m and n can be any number. Yeah. So you can write your answer in this form or this form. They are equivalent. They are equivalent. Any questions? So if you use the imaginary number I, then you may like this form. Or if you want to have trigonometric functions, cosine, sine, then you can easily turn this one into the form right here. Both are the same, are equivalent. Yeah, so it depends on your choice, whether you want to see your solution in complex numbers, whether you see it in real representation. Yeah, both are the same, are equivalent. All right, so I think this is the end of homogeneous equations. Because in here, I try to give you a full detailed solution to a homogeneous equation without any formula. We just apply the idea and we get all solutions. And you can do the same thing for any homogeneous equation. And then you can summarize, you can observe that in the end, for any homogeneous equation, this is the formula we have. So this is the one we use in practice. This is the one we use in practice. And if you try the same idea, you follow the exact same rules, you will see that we had those. Yeah, so now look at the formula we had. So this is from the note. This is the formula we have for homogeneous equations. When you have a homogeneous equation, the first thing you do is you look at the characteristic equation. This one is the characteristic equation. And you have, three situations. After that, you can see the three situations right here. And depending on which situation you have, you can apply the formula and get the solution. All right. So again, I don't go through this line by line. Let me go to the assignment and we practice some questions. So we have question 1, 2, and 3 right here. They are homogeneous equations. If you apply the same idea right here, you can solve all of them. But now it's time for the formula. So let's go from question number 1. Now, so this time I'm not going to solve this using the idea as we have done with the example. This time I apply the formula. So just apply the formula. All right, so let's say if you just apply the formula, it's extremely simple. The first thing you do is you look at the characteristic equation. So characteristic equation. You get t squared minus 5t plus 10 equals 0. If you solve this one, you see you get t equal 3 and t equal 4. You had two different rules, two different real rules, 3 and 4. Let's go back to the formula. So you can see in this example, we fall into the first situation, right? Because we had two distinct real rules. Because of that, this is what we need. This is what we need. So this is the situation we have in our question. Two distinct real rules, A and B. And the answer we have for y is the one right here. So very quickly we get the answer. So y is C1 to the power 3s, C2 4s. C1, C2 can be any constants. C1, C2 can be any number. So you know that, yeah. Yeah. This is 2 and 5, all right. 2 and 5. So this is 2, this is 5, yeah. 2 and 5. 2, 5, yeah. All right, so the answer we have is just 1. You can write C1 e to the power 2s plus C2 e to the power 5s, or you can write C1 e to the power 5s plus C2 e to the power 2s. So it can be 5 right here and 2 right here. It doesn't matter, right? Because C1, C2 can be any number. So you can consider 2, 5, or 5, 2. It doesn't matter. Any questions? So let's do one more in the assignment. Let me do 3. This is also a homogeneous equation. After this, we go to non-homogeneous equations. Now let's consider this one. Any questions? So now the first thing we do again, we look at the characteristic equation. Characteristic equation is t squared minus 4t plus 4t 0. You saw this one. Delta is 4 minus 4t, so you get negative 36. So you get t 2 plus and 2 minus right. The square root of negative 36 is 6i. So 2 plus 6i. This is 2 minus 6i. This example is similar to the example we considered right here, right? When you had 2 complex roots. Yeah, this one you have 2 plus 6i and 2 minus 6i, they are complex numbers. But this time we apply the formula. We don't need to go through, the setting v equals something. We apply the formula this time. And we fall in this situation. The first situation is when you have 2 distinct real roots, but we are not that. The second one is when you have only one repeated real root, meaning that you have only one root. This is when delta is 0. And the last one, when you have 2 distinct complex roots, this is when delta less than 0. A plus bi and a minus bi. Let me copy this one. So we fall in this situation. So we fall in here, right? A is the number 2 and B is the number 6. A plus BI, A minus BI. Because of the formula, now you get Y. So YS is E2 as A is 2, C1 cosine of 6S, C2 sine of 6S. C1 and C2 can be any number. Any questions? So this is the end of homogeneous equations. In summary, what you see for homogeneous equations is that first we have the formula for all equations, all homogeneous equations. Second, we see that when you solve any homogeneous equation, you always get infinitely many solutions. For example, this homogeneous equation gives you many solutions. In fact, we have infinitely many, because anytime you consider different C1, C2, you get a solution, a particular solution. So you have many solutions for any homogeneous equation. Now let's continue. So we go to there's some non-homogeneous equations. So let's go to non-homogeneous. So we have y double prime plus a, y prime plus b, y is f. F right here can be any function. So how to solve this one? How to solve this? You can open the note and look at example 3. After you go through this example 3, you can see how to solve non-homogeneous equations. In fact, it's also simple. Now look at this equation star. Let's say this equation is the equation star, and it's not a homogeneous equation because we have 6s plus 1 on the right hand side. It's not 0. So we cannot apply the formula we have for homogeneous equations. How to solve this equation? Now first, when you look at the right hand side, you see that f is a linear function. 6s plus 1 is a linear function. So the first thing you do is that you may guess that this equation has a particular solution, which is also a linear function. Of course, when you find a particular solution, it's not the end, because an equation like this would have infinitely many solutions. When you find only one solution, you cannot stop and say that the end. You need to find all solutions. But having a particular solution is good enough to find all solutions. So that's what we have for star. First, let me copy this one and put it right here. Now, this one you say, the first step I do is try to find a particular solution. In the first class, you may know what a particular solution is. A particular solution is any function that satisfies your equation. When you have a particular solution, you cannot say that's the answer because we may have many different solutions. So, but step one I do in here is to find a particular solution, and it's quite simple. You can see that the right-hand side is a linear function. So maybe we can find a particular solution. We see also a linear function. So I guess that we can find a particular solution in the form AS plus B. And then you try with that. So you just differentiate this one twice, and then you put them in here and you find A and B. So I skip that. You can easily do that. So from here, you differentiate Y. And then you put them in here, right? So maybe I do that for you. So Y. When you have a particular solution, you need to have this one. Right? You need to have this one because a particular solution is a function that satisfies your equation. So you can see this one is the same as the second derivative is 0, right? This is a linear function, so you have 0 minus 5a plus 6as plus b, 6s plus 1. 0 is the second derivative. A is the first, and then from here you get 6as plus 6b minus 5a is 6s plus 1. So from here you see that A is 1 and B is 1. So you can see you get a particular solution, right? So from here, you get right away a particular solution. So what P is S plus 1 is a particular solution. After you have a particular solution, how to find own solutions? You only need to set a new function u. So from here to get own solutions, you set u, y, minus yp. You set u, y minus yp. Then you can see that u double prime, u prime is, and u double prime is after you get a particular solution, how to find own solutions? Just set u, y minus yp and see what we get then. Now you have u prime and u double prime, and then you put them in, maybe I write y first. So from here, you say y is u plus yp, and then you get y prime double prime. And then you put them in this equation and see what happens to u, right? That's what we normally do. So from here, you put it in here, put y prime and y double prime in here. Then you get u double prime plus yp double prime minus 5 6 y 6s plus 1. So I just, after I got yp, I just want to know what happens if I set u y minus yp. Then I put y double prime and y prime in our equation star. And I say that what I get in the end right here is, in u, you get this one. Right? Because when you look at yp double prime plus 6yp minus 5yp prime plus 6yp, you get exactly 6s plus 1. So from here, you get this one. Anyway, so in u, you get a homogeneous equation, and you know how to handle it. So for this one, you can easily find u. So get u easily, right? And after you get u, you get y. You just consider u plus yp, and you get y. Yeah. So the idea is that, so let me put a summary right here. In order to solve a non-homogeneous equation, the main step is to find a particular solution, yp. And after that, you get all solutions. Yeah. So after you get u, you get y, and done. Yeah. So this is what we have for it. So let me put a summary right here. So this is the summary we have. You can see everything in the note. Yeah, in the note I wrote everything. The same thing, right? So this is what we have. Solve a non-homogeneous equation. This is what we do. So step one, find a particular solution. YP, this is the main step. This is the main step. And then step two. Step two is just, get the answer. Step two, all solutions are y is just yp plus u. What is u? Where u is from the equation. And for this one, you already knew how to find, right? Yeah, so that's the whole thing we have for non-homogeneous equations. The main step is to get a particular solution. After you have a particular solution, you get all solutions. You just add that particular solution to all solutions of the corresponding homogeneous equation. So now the main question is how to find, so the main question is how to do step 1, because this is the main step. How to do step 1. How to find a particular solution. You can see in this example, we find a particular solution by guessing it from the right-hand side. If the function f is a linear function, so we can guess that a particular solution is also a linear function. So in practice, we may do the same thing. Of course, if the right-hand side is so complicated, like you have so many different functions compiled together on the right-hand side, then it might be difficult for you to obtain a particular solution. The good news is that in here, we just focus on those very specific right-hand side f. So the function f we consider right here for non-homogeneous equation is the one you see right here. And this is what we consider in this course. For many equations you see in real life situations, the form you see right here is still helpful. So in the note you can see here we have a formula for finding a particular solution. Let me highlight it for you. So this is the formula we have. So how to do step 1? So basically the answer is we guess yp using f, and you may look at the formula. The idea behind this formula is exactly that. I think we need some practice for this formula because it looks complicated at first. So now first look at what we have in this formula. So assume that you have a non-homogeneous equation and the right-hand side is the one you see right here. The formula right here gives you a particular solution, but it's only the form for a particular solution. Now let's practice the formula. So I think we can do question number 4. So let's consider this one as an example. Now let's practice question number 4. So you can see this is f of s. And let's say you want to find all solutions. So what do we have for y, right? That's the question. You know that the answer we have for y is the following one. You have yp plus u. Yp is a particular solution of this equation of star. And you need to find one, and this is the main step. Finding a particular solution means that you want to find a function that satisfies this one. Any function. You know, we have many functions that satisfy this one. And in here, you need to find one. After that, you get own solutions. So that's the idea behind. How to find a particular solution. So this is the question. And for that, we can use the formula. So use the formula to find yp. And the formula that I mentioned right here is the one you see right here. This one. Yeah. So the formula we had, you can find in the notes. And now we practice it. All right, so that's for yp, and we need to go back to the formula. But let's see what we have for u. U right here is just u is just from the following equation. When you have 0 for the right-hand side, so u is from the corresponding homogeneous equation, and then you can see, you can easily find u, right? So this is just from the formula we have. You know, first you find the characteristic equation. So for this one, you have t squared minus t minus 2 equals 0. And then you get t, I think you get -1. And you get the number 2, right? And so if you apply the formula we have for homogeneous equations, then from here you get C1, C2. So this is the answer we have for U. Yeah. The remaining thing now is yp, right? So let's go to that. So let's find yp. And then after that, we get own solutions. Own solutions are the sum rate you see right here, right? Now let's get yp. Let's find yp. In order to find yp, I need to apply the formula right here. And when I look at this one, I say that I need to write the function f we have in the form, in the setting we see right here, because we need to run through the formula. So we need to know the setting we have first. So the function f we have in this equation is, let me first copy the equation we have. Copy this one and put it right here. Now this is f. And let's write it in the setting we have in the formula. So I write it as e2s phi s cosine 0 sine 0s. Why do I write this? Now in the formula you see let me copy the formula and put it right here. This is what you see in the formula for the right hand side. You can see that the setting we have for the right hand side is the one you see right here. Because of that, the function f we have in here, we try to write it in the same setting we have in the formula. First, we have e to the power 2s. So you have e to the power as, and right away you know that the number a is the number 2 right here. So this is exactly what we have for a. Yeah. So a is the number 2, you see. Why do I write 0 right here, cosine 0s and sine 0s? Because in the setting we have cosine and sine, but in the function we have, you see no trigonometric function, sine or cosine, meaning that we should have 0 right here. So b is 0. By the way, b is 0. So b the rule is very simple. If you see no trigonometric function in f, b must be 0. Like in our question, we see no sine or cosine, so it's just, so we have b equals 0. And now you know phi s right here is the function p, and 0 is the function q. So this is p, and this is q. What are n and m? N is the order p. Let me write that right here. N is the order of p. P right here is a polynomial, and you know what the order is. Right here in our example, phi s is a polynomial order 1. So n is the number 1. So I write 1 right here. Right? Let me put it right here for you. So n is 1. Why is that? Because n is the order of p, and p is phi s. Phi s is a polynomial order 1. Q of s is 0, is a constant. A constant is of order 0. So I write 0 right here, and this is the number m. This is m. M is the order of q. M is the order of q. Yeah, so that's the end of the whole setting we have for the right hand side. And we need to determine the setting because in the formula we need to know A, B, P, Q, M, and N. Now A is the number 2, B is the number 0, P is phi s, N is 1, is the order P, Q is 0, and M is 0. Now let's go back to the formula. The formula we have right here is for finding a particular solution, and it divides into 2 situations. The first one is B is not 0, and the second one is B is 0. Which one is the one we had in our question? Obviously, the second one, B is 0, right? So I copy this one. I copy this one and put it right here. Because this is what we had in our question. You see, in our question, you see B is 0, Let me highlight it right here. B is 0. You see no sine and cosine in f, which means that B is 0. So we look at the situation. In this situation, you have three smaller situations. When you look at this, you see we need to look at the characteristic equation. You see, in any situation, we need to look at the characteristic equation. Because of that, let me write the characteristic equation. From here, you know, the characteristic equation we have is t squared minus t minus 2 equals 0. Characteristic equation. Now, remember that you always have 0 on the right-hand side when you write the characteristic equation. When you have homogeneous or non-homogeneous, always have 0 on the right-hand side. So when you solve this one, you see you have, I think we saw this one before, -1 and 2, right? You had two solutions, -1 and 2 for the characteristic equation. Now see what we have in these smaller situations. In this, you need to compare A with the solutions of the characteristic equation and see which situation you have in these three situations. Now let's go back to A. In our question, what is A? Let me highlight it for you. So A is the number 2. Do you remember where A comes from? It's from the exponential function. You look at e to the power something in f. If you have that, you have A. If you see no exponential functions, A is 0. But in here, you have A is the number 2. And you can see the number 2 right here is exactly the number 2 right here is exactly a solution of the characteristic equation. And it's a single solution. So you know that in our question, what we have is the one right here. A is the number 2, and it's a single solution of the characteristic equation. You see, you write the characteristic equation, and you see that it has -1 and 2. So the number 2 is a single solution. It's not a double solution. Because of that, now you know why P is given in this form. So let me continue. So why P is the one right here. This is the form we get from the formula for a particular solution. So let me write it. Yp is SE, A is the number 2, so let me write the number 2 right here. R, what is R? Let me continue. I just write the whole thing and then we go back to R. N is the number 1, right? N is the number 1, let me highlight that. N is number 1. N is just the order P. P is 5s, and this is of order 1. So N is 1. So we write R1. What is R1? R1 is just a polynomial, order 1. Let me write that. So R1 is a 0 polynomial. of order 1. It can be any polynomial, order 1. When you have an arbitrary polynomial, order 1, you should write it in the form as plus b for some constants, a and b. All right, so far we follow the formula and we find the form for a particular solution. And the form we get so far is the following one. Yp is s e to s a s plus b. And this is the end of the formula. So the formula stops here and it gives you the form. But in order to find a particular solution, you need to find a and b right here. How to do that? Of course, now you need to do the old thing as we did before. You need to differentiate yp twice and put them into this equation and find a and b, right? So now, so this one is we need to find a and b to get a particular solution. So this is just the form. It's helpful because the formula gives you the right form. Let's say in these two forms, if you follow this one, in the end you will get no a and b. But if you follow this form, in the end you get a and b. How to find a and b is very simple. You just to find a and b, we put yp into, of course, the equation we have, the one right here. And then you get 5se to the power 2s. Yeah, it's similar to what we did before in here. Let me go back to yeah. So after you get the form, you just put yp into and you find a and b, right? Similar to that. So I skip that. I skip the part right here. We just do the same thing. This is the form we have for our question. And then after that, you get a and b. So a and b for my question is this one. Let me put them in here. It has time to find a and b, I skipped that because, you just differentiate yp once and twice and put them in this equation, similar to what we did before. It has some right here. After you find a and b, you get a particular solution. All right, so to put a summary for the whole thing, the main part is to find a particular solution. And the formula right here gives you the form only, the right form. If you don't follow this, you may end up with an incorrect form and you cannot find any parameters, A, B, or C or something. So you follow the form, the formula, you get the form. But that's just the beginning. After you get the form, you need to put yp into the equation you have and get specific, the exact yp. It has some right here. And after you get yp, you get all solutions. So all solutions you have is this one. And the final answer we have for our question for all solutions is just yp. So let me see which one is yp. I think we had s, right? So definitely this one. Yeah, this one. So this one is the answer we have for all solutions. After you get yp, that's, almost the end, right? The one right here is exactly what you get for yp, right? And the one right here is what you get for u. This one is from the corresponding homogeneous equation. And this one is yp. All right, so that's one example. If you solve this question completely, it takes a lot of time because, yeah, the main part right here is to find yp. And in order to find yp, first you follow the formula and get the form. And after you get the form, you need to put yp, the form, into the original equation to find all parameters A and B. And after that, you get all solutions. We still have time, so let's do the last question. Question number 5. But I do only the part for finding the form only. So I find the form only. And after the form, you can, you need to find all parameters A, B, and get an exact particular solution. So let's do question number 5. If you just find the form, it's not so, it may be quick, right? So look at this one. F is the one right here, you see. You see F. And again, I try to write this in the same setting. We have e to the power something. In here, I see that I had no exponential function, so I had e 0s. But I see psi, so b is not 0. 0 cosine phi s plus 2 psi phi s. Right? So A is 0. A is 0. And B is the number 5. You see cosine, you see sine. B is not 0. You see no exponential function, A is 0. All right, so what is P? This one. What is Q? This one. P and Q right here are just constants. The order is 0, right? So the N is 0, M is 0. N is 0, M is 0. The order of a constant is 0, right? N is 0, M is 0. So that's the whole setting. So let's look at the formula. In the formula, you see we had two situations. B is not 0 and B is 0. This time we found in B is not 0. Do you remember that B is the number 5? So I copy this one and put it right here. Because B is the number 5, let me highlight that for you. B is 5. B is from psi, right? So B is not 0. Because of that, we need to look at these two situations, two smaller situations. And for any in here, you need to look at the characteristic equation. Because of that, I need to go back to the equation and see what the cluster of the equation is. You see, we had t squared minus 10t plus 25 equals 0. Remember that I always write 0 on the right-hand side of the cluster of the equation. When you solve this cluster of the equation, what do you get? You get only one real root. It's the number 5. T equals 5 is the only solution. Let's go back to the formula. Now I need to compare A plus BI with the solutions of the quadratic equation. A plus BI is, what is A? A is 0, B is 5, do you see them? A is 0, B is 5, so A plus BI is 0 plus 5i. 5i is not a solution, right? 5i is not equal to 5, so we fall in this situation. A plus BI is not a solution of the quadratic equation, because I see we have only one number 5 for the solution of the quadratic equation. Anyway, so now we look at this form. And write what we have. So now you see yp is e to the power 0s because a is 0. A is 0. Rk, now what is k? K is just the mass of m and n. K is mass of m and n. N is 0, M is 0, so mass of 0 and 0 is of course 0. So K is 0. So I write R0, Rk, R0. Cosine B is 5, H0, B is 5. What are R0 and S0? They are just any polynomials of order 0. And you know that when you have a polynomial of order 0, you have a constant. So this guy is a constant, and this guy is a constant. So this is the final answer for the form we have. R0 is any polynomial of order 0, and you should have a constant for that, the same for S0. But you cannot write the same constant. I need to have two constants, A and B. Done. So the answer we have for the form is the first one right here, not the second one. If you follow the second one, you put it in here, you will see no A and B. Check that. All right, so the form we have is this one, and then you need to put this into the original equation and find A and B to get, a particular solution. I think that's the end for today. Yeah.